Okay, one last video with interpretation fact. So far we've computed everything, we've done all the proofs, but here is one more way you can interpret the final answer. So we had the final answer, f of x after training theta infinity, and we computed its mean and variance, and we got some answer. So it's a Gaussian distribution, and we know its mean and variance according to some formula involving k and the training data. Here is another fact. The distribution of this guy, so thinking of it as a random variable, its distribution is equal to the conditional distribution of something else. And what is it equal to? The conditional distribution of what it is at time 0, so on initialization, conditioned on. What is it conditioned on? Conditioned on the event that the training data is perfectly fit. So the event that the training data is perfectly fit, let's write it like this: f of xi theta 0 equals f of yi for all 1 less or equal to I less or equal to n, and examples. So if you take the model on initialization, that's some random model, it has some, there's some event that it fits the training data perfectly just by chance. And if you look at those distributions, so the conditional distribution conditioned on this perfect training event, that's exactly what you get after training. So before training and getting all the data exactly right, or after training, are the same thing. So what you can think of is what the model does is it, as you're training, it sort of fits the training data better and better, but leaves all the other stuff like sort of untouched in a certain high dimensional sense. And so what you end up with is, after training, you get what you started with, but conditioned on this funny event. And the way you notice this is you compute the distribution. We did that. That was some formula. You can compute the conditional distribution by using the law of conditioning Gaussians, which is not so complicated. And it turns out they're the same formula. So the reason the distribution of this is equal to the conditional distribution of this is because we can calculate both and they're equal. So that's a bit of a crazy miracle. And I think the reason it happens is because the kernel K appears both in our training dynamics and in our time 0 dynamics, our initialization. So, and because it's the same kernel K in both, when you do the multiplication in the proof of Theorem 9, you get some cancellations with the K that mean this formula will work out. And so I think it's kind of a funny quirk. It's kind of a miracle thing to me. I don't see an easy way to prove why this would be true, except for to calculate both. So it's a good way to think about what the model is doing.